Record.
All right, welcome everyone. We have Gord Cook giving us another presentation on HVACs. And so I'll just turn it over because we usually run right up to the hour. So
exactly. Sorry about that. So thanks very much, folks, for listening again. That's very kind of you, generous of you to take your, I guess it's Thursday afternoon now, or at least afternoon here in Ontario. So I'm coming to you from Cambridge, Ontario, just west of Toronto. Nice to see folks from across the country. Lauren Lipka, obviously a familiar name. Hi, Lauren. Nice to see you. This is a course that, or at least a little session that Lauren could easily head up with his level of knowledge. And John just said to me, could you just put some slides together on HVAC to create a bit of a conversation? So I have some slides in each one of those categories. That is the H, heating, the V, ventilation, the AC air conditioning. I'm going to term that more in terms of dehumidification, because I think that's more important in some of the communities, specifically, Victoria and so on, or at least on the West Coast. So we'll do a few slides and then time for questions, I guess. And hopefully I hit the mark. And if I'm not, chime in, by all means, just break in and let me know that you want to ask a question. And if there's something comes up on the chat, John, don't be afraid just to interrupt me and say, hey, Gord, there's a question. Are we all good with that?
Yep, that works.
Great, thank you. And what I thought I would start with, and it's an interesting, or at least an important topic of conversation, which is the basics of heating sizing. That is, how much heat do we actually need? And then a little bit on some of the common types of, I'll call them high performance HVAC systems, which will point to some options that I think are now available to your communities, certainly in new construction, but even in existing housing. I think there's some opportunities for some of the changes that have taken place. I want to talk specifically about some hybrid, and then I do want to talk ventilation and dehumidification. And I know in the last call we touched on ventilation, so frankly I put in some more slides on ventilation, just to highlight that. If hopefully everybody's okay with that. And I just want to be, I guess, clear that I'm pretty much fuel agnostic. I don't really care which fuel people use. Obviously, in your cases, in your many of your communities, you don't have a lot of choices often. I think it's fairly clear you have electricity available for the most part, but it comes to you sometimes very expensively. That is, you're generating it yourselves, or you're at the end of a long, expensive line. So, but one of the things I do want to say, if we are going to use electric, as opposed to straight electric resistance heating, which can never be more than 100% efficient, there are now technologies, heat pump technologies, that I think are ready for your communities. I wouldn't have even said that 15 years ago, not that they weren't available, but I would say that the heat pump technologies that are now available are more applicable to First Nations for a bunch of reasons that I'll try to indicate to you. And then where you have, obviously down Windsor Way, you probably do have access to natural gas. Most of you would have access to propane, except again, it might be very expensive and you have issues perhaps with reliability of delivery. Hopefully most of you are off of oil. I think we can all agree, well, hopefully we could agree that oil is, probably not the right choice, frankly, in any house in Canada, let alone First Nations. And I suspect some of your communities are using wood as a supplement, so I've added some pieces on wood. Solar we would see as a choice to supplement electricity. That is, I wouldn't necessarily talk to you about solar heating, and I can come back to that if you want, if somebody has a question on that. And then the combinations thereof, I guess. And then also on this same slide, thinking about the distribution choices. That is, first we choose the fuel, or at least maybe the fuel is chosen for us. And then we think about, how am I going to distribute the heat? So is it central forced air? Is it zoned? Or maybe it's mini ducted or mini split type systems? Or is it radiant heat that we could be using? Could be in-floor or baseboard heating, or ductless systems that I'm going to touch on today. I think are a tremendous new opportunity. And you're going to say some of you are already using it, so maybe it's not new, but I think it needs to be highlighted. Let's put it that way. And again, probably last on the list would be space heaters, individual space heaters. They tend to be problematic from a safety perspective and so on. So those would be the choices. And I wanted to start with the sizing conversation. And what I want to try to do is show you how relatively simple this is to do. That is, it's not that difficult to figure out how much heat on the coldest day of the year a building needs. And it's a CSA standard. It was just recently rewritten. I say recently, 2012. I happen to be the chairman of that committee. Not that that means much. It meant I could delegate all the work, but it really helped simplify, I will say, the concept of how do I size. And on the left-hand side, not that you need to know these formulas, but simply to know that there are three basic formulas. That is, with these three basic pieces of math, you can size both the heating and the cooling system for any house in North America. It's pretty simple. And if, for example, you wanted to know how much heat is flowing through a wall, for example, or a ceiling, that's first formula. All you'd need to know is the surface area of the wall, the temperature difference across the wall between the inside temperature and the coldest day outside. And of course, the coldest day changes based on who we're speaking to. If we have folks out in Victoria, BC, cold for you guys might be, 5 degrees Celsius or maybe 0 degrees Celsius. I saw somebody from, Dave from north central Saskatchewan, we're talking at minus 30. I get that. So you have much greater temperature differential. And so it's the surface area times the temperature difference divided by the R value of that wall. That is the thermal resistance of that assembly. And you can start to imagine, I'll just show you an example of that. If I thought, for example, how much heat flow is there through an attic on any given day? Now, most of the industry is still in imperial metrics, that is square feet. So in which case we have to switch from Celsius to Fahrenheit. Sorry, you got to stay with one set of units. And if you don't want to do square meters, you want to do square feet, then you got to go back to Fahrenheit. I still think you'll be okay with that. The good news in Saskatchewan, minus 30 is the same in Celsius as in Fahrenheit, or at least close to that. I think it's minus 38 is identical or something like that, but maybe less confusing. But if I wanted to know the heat flow across an attic floor or the ceiling of a house, it's pretty easy. It's that 1,000 square feet times the temperature difference. And if it was 70 degrees inside and 10 degrees outside, again, that's 10 Fahrenheit. And some of you would say, I get colder than that. Yep. Some of you would say, I never get that cold. But you would plug in what's called the design day temperature, not the coldest day ever, but what represents statistically, the coldest day, 50 coldest days of the year, if you will, 50 coldest hours, sorry, of the year. And you would divide that by R30 in this case, if we said we had R30 in the attic, the insulation value. And as you can see, that's pretty simple, straightforward math. That means you have 2,000 BTUs, whatever that is, British thermal unit of heat flow every hour. Every hour, 2,000 BTUs of heat is leaving the house, heading up through the insulation, through the drywall, through the insulation, and to the great outdoors. And of course, you start to imagine if I had a 40,000 BTU furnace, 2,000 of those BTUs is needed to replace the heat that's being lost through the ceiling. And when you do a heat loss for a house, you would do, okay, let's do the heat loss through the ceiling, let's do the heat loss through the walls, let's do the heat loss through the windows, let's do the heat loss through the basement. And all of these, in today's world with a pretty simple Excel spreadsheet, or there's actually software packages, but even with an Excel spreadsheet, you can get a really close estimate of your design day heating requirements in 45 minutes to an hour on a pretty straightforward house. Just if you knew the dimensions of the house, really all you need to know is the dimensions of the house, and also, I guess, the R values or the predicted R values. You also get to imagine, what if I wanted to make that heating number lower? What if I didn't like 2,000 BTUs of wasted heat? Well, let's go ahead and double the insulation. For example, see the guy here on the right spraying insulation. If I doubled the amount of insulation, you can see this formula, I would have cut the heat flow in half. And that's important to understand. You think about new houses in your communities, perhaps that have been built in the last 4 or 5 years, they undoubtedly have more insulation in walls. They undoubtedly have more insulation in ceilings and better windows. And generally speaking, new houses built today, I'm going to say built to National Building Code. I know some of you don't necessarily use the National Building Code per se, but I suspect you're using similar insulation values. New houses today use or waste or lose roughly half the amount of heat that a house built even 20 years ago did. Wow. So in the last 20 years, we've cut in half the heat loss of a house. And similarly, as I said, if you took 1,000 square feet of walls, you think about a 40, say a 30-foot wall times 8 feet high, 30 times 8, that's 240 square feet. And I've got 4 walls on that house. So if I had a 30-foot cubed house, then I would have roughly 1,000 square feet of walls. The walls, of course, are insulated typically less than an attic. And you'll notice here the walls, therefore, would be 3,000 BTUs because they're insulated less than, say, a new attic. And what I'm trying to get across here is within your communities, you would be able to do a heat loss on a building in fairly straight order just by using this formula and one other. So pretty straightforward.
We have
Yep.
a question
Sure.
here, or maybe a clarification. Dave's asking, is this effective R value that we're talking about in this formula?
Oh, Dave's way too advanced. In this formula, yes, Dave, you would use, and I have simplified things here. Yes, you would use the effective R value. And for those who aren't familiar with that term, we did that kind of, I think, in the last session in building science, that when we say your wall's insulated to R20, we know the cavities are insulated to R20, but every 16-inch on center, you have a piece of wood, and that piece of wood is only R5. So I have to take the weighted average of that wall. That's called the effective R value. So just for example, for Dave's benefit, that would be roughly an effective R value of a standard 2x6 wall is not R20, it's R15. So if I plug in R15, 1,000 times 60 divided by 15, my new heat flow would be 4,000 BTUs. So good catch, Dave. The actual heat flow through that wall is not 3,000 BTUs, it's 4,000 BTUs. But I think you could start to imagine in the grand scheme of things, that's not a huge impact. That is a 40,000 BTU furnace, gas furnace, for example, or a propane furnace, or a 15 kilowatt electric furnace, which is roughly 40,000 BTUs. Only 3,000, or in this case, 4,000 of those BTUs is going through the walls. So, but thank you for that. Yes, you would use effective R values in the spreadsheets. Thank you for that.
One other comment. Is this typical what we're going through for residential applications only?
Well, this is residential. The same heat loss applies to your community centers, schools. That is, the physics of heat flow is exactly the same. Obviously, different construction methods. Maybe it's a block wall and what insulation values of the block wall, but you would absolutely take exactly the same formulas to do a heat loss for any one of your, let's call it community buildings as well. Any building, the physics of heat flow is the same, whether we're talking residential or commercial buildings. Hopefully does that answer, do you think, the question?
Thank you. Yes.
Okay. So yeah, the physics does not change. These formulas are the same formulas used in commercial. The only thing that would be different is you'd need to know the effective R value of those building assemblies. Good. And what that means is on this list is if you want to get the sizing right, and I'll go right back to that community building, you'd want to know you had the right insulation levels. So in new construction, they're specified on the plans, you've got it. In existing buildings, you'd have to do a little bit of investigation, maybe peek your head into the attic, or take a thickness of the walls and try to get a sense of what might be in the walls for insulation levels, but you want to know the insulation levels. The big issue, windows have their own conduction heat losses, much smaller. For example, a typical Windows R3 conductive losses. So you'd want to know the right window data. So you'd need some stats on the windows. And then what I haven't shown you is the air leakage component. So the air leakage component is a little harder to figure out. Lauren and I do blower door testing. Some of you know what that is, which is you do air tightness testing on the building. And from that, you can predict the heat loss associated with air leakage. And here's what you need to know. I probably covered it in the last session. About 30%, nominally, 30% of the size of your heating equipment is needed to replace the heat that's being wasted or lost through air leakage. So there are formulas that would help you determine that, but just in the back of your mind, say, my walls are 4,000 BTUs, my ceiling's 3,000 BTUs, or whatever those numbers are. The air leakage represents about 30% of the total heat loss of the building. Imagine again that 40,000 BTU furnace, 30% of that, 12,000 BTUs, would be needed to replace the heat that's being lost through air leakage. And you can start to imagine that we'd like to make buildings tighter to get rid of that waste. And that's true in commercial buildings, and that's true in houses and townhouses and so on. In commercial buildings, it can be worse because as you get to taller buildings, say 3-4 story buildings, there's more air leakage because of warm air rising, leaving those buildings. The key out of these few slides, and sorry for the long conversation, is to say you don't really need to guess. You can guesstimate, or you can do a fairly simple, quick, how big a furnace does this building need is the key out of that slide. And then from there, you would say, I wonder how much, I'm showing both heating and cooling. Not all your buildings, your schools might be cool, I'm not sure, but probably most of your houses aren't. Many of your climate zones, you don't need much cooling. But to determine how much heat I need to a specific room, so I do a whole building heat loss, that is the walls, the floors, the ceilings, but I can do the same calculation for an individual room. You'll see here, this room has one exposed ceiling. I would take its surface area. I would take the wall and its surface area, and I would figure out the BTU loss in that room. And then I can describe from there, if I'm using a forced air heating system, exactly how much heat and how much air do I need to each individual room. Or in the case of electric heat, how big an electric baseboard heater do I need in that particular room? So it means we can stop oversizing systems when, typically people, well, I'll just put in a 1 kilowatt baseboard heater, 1 kilowatt, 1 kilowatt, 1 kilowatt, and all of a sudden you need a huge amperage service size, whereas you found, well, this bedroom only needs 250 watts and this bedroom only needs 500 watts. Now I can reduce my service size and obviously bills go down and so on. So, and the nice part is when you've doubled insulation values, you've cut the heat flow in half, and now your houses would need a less, if you're using electric baseboard heat, would need smaller electric baseboard heaters in each room, and they'd be less expensive to operate. And so we would say that provides new opportunities, sometimes some challenges in terms of making sure we get it right. People sometimes don't believe that these size of heaters are actually going to do the job, but we can describe pretty quickly the heat loss, heat gain characteristics of a particular room. And that, as I said to you, gets you to some new opportunities. On the left-hand side, for those of you who do have access to natural gas, there's some great new small capacity. This particular furnace, its maximum output is 38,000 BTUs. And it can actually run down to as low as 18,000 BTUs. And if you are building new houses to the latest codes, this size of furnace is probably appropriate for many of your houses because you have well-insulated houses, modest in size, and I don't need big honking blowers down in basements anymore, blowing thousands of CFM of air around a house. You can use really modest size equipment. The one in the middle, I'd mentioned to you the idea of heat pump technology, and I'm going to come back to that in a second, but these are refrigerant based. This happens to be Fujitsu, but there's Mitsubishi, Daikin. There's about, well, I would say the top 3 brand names are Mitsubishi, Fujitsu, and Daikin, and they now all have systems that I'm going to say are plug and play friendly. That is, in the past, these would have been difficult to apply in remote communities. Now, all of these companies have good training programs and good systems in place that make these kinds of systems plug and play. You'll also notice that they have different styles of heads. That unit to the right, where it says Fujitsu, that would be outside. That's a heat pump. It looks like an air conditioner, but it's actually a heat pump, which means it gives you both heating and cooling performance. The units on to the left of that are the differences, different types of equipment you can install in the house. Most of you would have seen that middle one before, what they call a head that would go on the high wall, for example, side wall of a house, say in the living room. But the other two, one is a ceiling cassette, so it installs in the ceiling, so it's not as visible. The bottom one is actually a little mini ducted version, one that I want to chat with you about a little bit. And then if you have gas available or propane, we could start to think about using boilers or tankless water heaters to not only heat our hot water, but to heat the house, to use, for example, some panel heaters, to use some in-floor heating, for example, in a basement, or a hot water air handler. So we're seeing new opportunities that I think can be useful in your communities because you can actually simplify some of the operation. And again, if you only have access to electricity, the technology that makes the most sense is that one there in the middle. And I'll come back to that, as I say, in just a little bit. I won't spend too much time on this because, again, I'm not sure how many of you have access to natural gas, but I just wanted to make the case that every gas furnace now sold in Canada, the minimum efficiency requirements for gas furnaces is 95%. So in my lifetime as a 20-year-old, you could still buy a 60% efficient furnace. Now the minimum is 95%. That is, for every dollar of gas you buy or propane you buy, you get 95 cents worth of heat. What's really nice in your communities is these are sealed combustion direct vent. There's no natural draft or natural drafting or aspirating chimney. And that's a really important safety concern if you are using a fuel like natural gas or propane, to make sure we have safe operation. These devices are indeed safer. There's no chance of plugs by leaves, no chance of a squirrel building a nest in the vent in the chimney. So they provide a much safer option. And they all have these new, what are called ECM fan motors, EC fan motors, electronically commutated, far more electrically efficient. And again, in your community, some of you would have very high electrical costs. These furnaces, to move this air, use about 1/5 the amount of electrical power. So they're efficient on the gas side, but they're also efficient on the electrical side. So that's pretty useful. And of course, they are, I shouldn't say of course, but they are smaller is the point. And what I was suggesting to you, that rather than, or in a community, if you didn't have natural gas, it would be quite possible to put in an air handler, a forced air system, with an electric resistance coil. So you'll see that there, the squiggly line on the drawing. Or in fact, you could use a hot water coil. So if you didn't want to use gas furnace, but you had availability of propane or natural gas to do your hot water, a tankless water heater can drive hot water through these systems. And now you have one fuel, one vent that's actually, in this case, using hot water both for showers and cooking, and also hot water to heat the house. So it's a pretty nice technology, a fairly straightforward technology that requires a plumber as opposed to a gas fitter, if you will. So still have to put in the gas appliance, or again, I could go simple electric. And if you have an electric furnace, Manitoba is really good at this. You guys do a lot of electric furnaces in Manitoba. And you have relatively cost-effective electricity, at least in mainstream communities. I'm not sure in your individual communities. But again, marrying this up to a heat pump, I keep using that term heat pump, but I'll come back to that. As I say, I'll keep coming back to that. And again, the new boilers, similar to gas furnaces, historically 60%, now they're at 90 to 96% efficient. And again, they're sealed combustion, closed loop systems, far more efficient, far safer, much better technologies that we want to get to. And here is that idea of using a combo system. using the white box on the right. There is the boiler or water heater. So it has the ability to heat hot water for showers and cleaning, but it also, you'll notice the pipes. So the pipes going to the right, the red and the blue pipe are going to your showers and sinks and so on. The copper going to the left is the same hot water, at least equal hot water, going to the air handler. So rather than putting in a traditional furnace, you put in an air handler. And I suspect the reason I mention these is because once you've invested into the efficiency of, say, a really good water heater, 95%, let's go ahead and rather than buying yet another expensive gas appliance, let's just go to a much simpler air handler. And I don't have to worry about venting it, and I just need my plumber to do the connection. So we're big fans of combo systems is where we like to get to. It is important to understand these systems do need to be matched. And there's a CSA standard. So if you as a community were buying or specifying these, you would always ask the manufacturer for their combined effect and to make sure that the water heater is matched properly with the air handler. It doesn't have to be the same company, but they have to show that they tested the two appliances working together. That's the important part. So Navien, for example, if you're using a Navien, it's paired with certain air handlers. Rinnai is paired with different air handlers. And again, all on the presumption that you have available to you natural gas. And now we move to the idea of heat pump. And I want to center on the drawing on the schematic on the far right. For those who don't know heat pumps are electrically driven device. And rather than making new heat, they're simply extracting heat from the outside air, upgrading it through the magic of refrigeration, and delivering it into the house. Heat pumps 20, 30 years ago were not well suited to Canadian cold climates. They would have worked fine in Victoria 30 years ago, but they would not have worked in northern Saskatchewan or in Manitoba. There are new, great, low temperature heat pumps that are designed specifically for our cold weather. They have what's called a variable refrigerant flow, and they're able to manage the refrigerant and work really nicely in cold weather. You get the added bonus if you move to the left that you get summer air conditioning. Again, many of your climate zones don't have big cooling loads. I understand that. But again, in your commercial buildings, let's call it the community buildings, schools, offices, and so on, where there's a lot of people load, a lot of lighting load, or maybe even server loads, you may indeed want air conditioning, in which case heat pump would satisfy that requirement. The big key to this slide is these appliances are 300 to 400% efficient. That is, for every dollar of electricity you buy, you get $3 to $4 worth of heat. Now, electricity is still really expensive, especially in many of your communities. But if you are going to have to use electricity, would you rather use it at 100% efficient, which is electric baseboard, or would you rather use it at 300% efficient? And hopefully the answer would be, I want to get $3 worth for every dollar that I spend. So you, one, make your building more efficient, put in more insulation to reduce the heating requirements, but two, switch to heat pumps. I'm showing in this case air source heat pumps. That is, they're taking heat from the outside air. Many of you would know there's ground source heat pumps as well. I'm going to say to you on the houses, individual houses, air source heat pumps tend to be more cost effective. That is, unless you're drilling community loops for the ground source, the air source heat pump is less expensive to install than trying to install heat pump loops. In a school, ground source heat pumps make sense because the infrastructure is there, the maintenance folks are there to do it. But I'll say again, these heat pumps work better for us now because the manufacturers have simplified the installation and do offer training, because you still need somebody who's familiar with and is qualified to do refrigeration work. And but that's more available than it's ever been, and the tools are now available. So this is a really nice technology, and I can't stress it enough. And just showing it here again, this just to highlight, this coefficient of performance of 3 to 400% efficient gives you that air conditioning. The units do need to be up off the ground a little bit past snow load. The issue with these guys is they have to work harder as it gets colder outside. Okay, they have to work harder. And in the very coldest of climates, you might say, do I have enough heat? And you probably are going to look for some supplemental heat for the very coldest of days. So imagine most of the winter, you're at 300% efficient, but on the coldest days, you're going to drop back to, say, 100 or 120% efficient because these guys are working much harder. I'm not saying don't use them. What I'm saying to you is understand that the efficiency does drop as it gets colder outside. Just as a little example of that, look at this bar on the red bar. This particular device has a nominal capacity of 18,000 BTUs, a ton and a half. Notice at 47 degrees, if you go across to the right, its capacity at 47 degrees Fahrenheit outside is 22,000 BTUs, but as it gets colder out, its capacity drops. It only gets you 14,000 BTUs. So if your house has a heat loss of 22,000 BTUs on the coldest day, you'd need to put in a bigger heat pump in order to get this to work. This is the traditional heat pump, if you will. If I go down to the next red line, you'll notice if I go over to the right again, if I needed 22,000 BTUs at 17 degrees Fahrenheit, I actually have to put in a 3-ton system. So you think you only want to put in a 1.5 ton system, but because the heat pump doesn't get you that capacity at its coldest temperature, you're in Manitoba, and in Manitoba you're going to go, we get colder than 17. I know you do, so it'd go down even further. The good news is, and this is just showing you that sweet spot of the heat loss of the house and what's happening to it versus the size of the heat pump. So there is a little bit of a burden, if you will, to figure out what's the sweet spot of what size heating system do I need. And I would say to you, it would be absolutely okay to put in some supplemental heat, to say I'm going to use the heat pump most of the time, but for the coldest days, I'm going to put in a wood stove, or I'm going to put in a electric baseboard heater. That could work for me as well. Here is a cold weather heat pump. This is a cold climate heat pump. This is a Mitsubishi. Look at this device. At 45 Fahrenheit, its capacity is 38,000 BTUs. And at -5 Fahrenheit, and you're going to say I'm still colder than that, boy, efficiency hasn't dropped that much, or at least its capacity hasn't dropped that much. It's still 33,000 BTUs. If you went colder, I'm not showing colder, but if you went colder down to -35, okay, its capacity's dropped to only 20,000 BTUs. On the far right is its coefficient of performance. Notice at 45 degrees, it's 3.4 times. That is, it's for every dollar of electricity, you get $3.4 worth of heat. When it gets to -5, now it's only 1.6% efficient, if you will, or 1.6 times efficiency. And in fact, its efficiency drops to around 1. That is, you're getting, for every dollar you spend, you're getting $1 worth of heat. But you can imagine most of the winter, I have this really nice 2 to 3 times the efficiency of electric baseboard. So don't get discouraged that I can't get the same efficiency with heat pumps. What we're saying is for the bulk of the winter, you're going to be saving really nice dollars. And maybe on the coldest days, I need a little supplemental. Here's the ground source opportunity. The ground source tend to be more stable because ground temperatures are more stable. The deep ground temperature, even in Saskatchewan, is still above freezing, right? You go down 8 feet to below the frost line, you're still above freezing. So you can get better performance out of a ground source heat pump. The issue is you got to drill these loops and maintain these loops in the ground. And that there's technology to start off, and then there's maintenance. So I think they're better suited for community buildings than it is for individual houses, would be my point. Some communities might be doing, well, I've seen it, doing community loops. So they drill a bunch of loops and then all of the houses draw off of those loops. That's another way of looking at it. But I like this idea, right, of supplementary heating. So there in the central room, say the great room or the living room, you have a heat pump head that does all of the heating for that space and maybe a little oversized. And you use some, I'll show you in a second, some transfer fans and so on. And then you would supplement this in the bedroom, say, with some baseboard heat. So the bedrooms stay reasonably warm and just with this heat pump running in the one room, and then baseboard heaters. And Lauren out in New Brunswick, you guys have seen a lot of this in manufactured housing. The manufactured housing guys are doing a lot of this. Maybe one or two of these heads, not one in every room, but maybe two of these heads in a house, and then supplement individual rooms with baseboard heaters. That's a great way to go. Or you could, in fact, do these technologies, these new refrigerant technologies, do allow you to have one outdoor unit. So you'll see the unit bottom left there on the outside, but then multiple units inside. So in the living room, I'm doing on the right-hand side there, I'm doing that head on the wall. In the dining room, kitchen area, I'm using the cassette in the ceiling. And then in the bedrooms, I'm using this little mini ducted system. So maybe it's 3 bedrooms. Each bedroom gets a little small duct running from this device that's, say, hidden in a closet, in the ceiling space in a closet. This is the way I heat my house. I have a 1,500 square foot on the main floor, 1,500 square feet. I have a little loft upstairs, but I heat my house with exactly this strategy. Now, it's a very efficient home, but I heat my house with my bedrooms get little mini ducts, 3 bedrooms, little mini ducts. The main room has that head that you see there on the right, and I actually have a head in the dining room just on the wall, but I could have used that cassette. And I see this as a pretty interesting technology these days that I think is applicable in your communities, is where I'd go with that. And then I will say, hopefully it's you guys are accepting of this. Wood heating is a good supplementary heat. Wood heating, I think you would agree, because of the attendance, you have to stoke it all the time, may not be ideal as the primary heat source. But if you imagine a heat pump doing centrally and then a really good airtight wood stove, I'm going to say you should switch all appliances to EPA rated stoves, always using seasoned wood. There's a little bit of a conundrum here. The newest wood stoves are way more efficient than older wood stoves, but they really do require seasoned wood. Now, all fireplaces need seasoned wood, but these guys are even more prone to that. They really struggle to give good heating unless you've got seasoned wood, which means as a community, you need to think about, how do I do that? How do I manage that? And then if I am using these, say, in a central location, if I had an HRV that was moving air around the house, or if I had transfer fans, some simple bathroom fans or transfer fans moving air around a house, could I use that? And so there are the great new technologies, the advanced combustion, catalytic conversion, so on, that create these really nice, great flames. I'll move along a little quicker. The point here is seasoned wood under 20% moisture content, which means you probably need covered storage, typically 6 to 18 months. And when we say seasoned, we mean under 20% moisture content. And on the left, you'll notice, boy, the dramatic reduction in the air quality in your community. If you switch folks from using the old inefficient stoves to the new, you've cut emissions by about 70%. Really pretty, well, this says 50%, but you can cut emissions by as much as 70%. So very, very powerful to get there. Again, seasoned firewood, making sure it's properly stored is where we want to get to. And then I did want to touch, we have a little bit remaining, but a little bit on ventilation. And I just wanted to touch back on, how much ventilation do we need? And in codes and from long history, we know that ventilation is basically needed for the people. So how many people do you have in the house? We often use the number of bedrooms as an example of that. Some of your communities, you would say, no, we have higher occupancy. That's fine. You simply count the number of people and you multiply by 15 cubic feet per minute. Think of it as basketballs of air. Every person in schools, it's 15 to 20 CFM. In offices, it's 15 to 20 CFM. In houses, it's 15 CFM per person. So that's how much air you need on a daily basis. Now, it's always useful, it's always useful to, I don't know what happened there. I'll get rid of that. So 15 CFM per person is what you need. And then in addition to that, we would say you still need the capacity in bathrooms for either 20 CFM continuously or 50 CFM intermittently. Kitchens, 60 CFM continuous or 100 CFM intermittent. There's a lot of pollutants coming off of stoves, cooking odors and so on, and grease and fats and volatiles. So you really would like to exhaust at the source, either with a continuous exhaust port from there or a separate range hood or bath fan. And I mentioned last time, don't be discouraged. Of course, I want you to get to the right-hand side, HRVs or ERVs, but there's absolutely nothing wrong in existing housing to solve ventilation issues, air quality, moisture issues in your existing houses. And you would specify a good, quiet bathroom fan. And how much air? 15 CFM per person. If you have 6 people living in a house, 6 times 15 equals 90 CFM. You would want to put in that house a fan that had the capacity to run at 90 CFM quietly on more or less a continuous basis. 90 CFM. If you only have 3 people in the house, now it only needs to run at 45 CFM. And many great fans from Broan, Newtone, Panasonic now have 2-speed fans. So you run the fan at low speed all the time, and then when somebody goes into the bathroom, they either flick the switch or there's an occupancy sensor that says, let's go to high speed. You could even think in the middle about a central exhaust fan, a fan that takes air from, say, 2 bathrooms or the bathroom and the kitchen. That'd be fine too. So all your houses need capacity for ventilation. They don't have to be an HRV or ERV, but at least a good, quiet fan is what you like to get to. And as I say, these new Energy Star labeled fans, look for an Energy Star labeled fan, and that's going to get you good performance. In terms of HRV, there's kind of, I'm going to say 2 installation options. One is exhaust from bathrooms and kitchens. And if you have a forced air heating system, simply take the fresh air and dump it into the return air system of the furnace. That's called exhaust or partially ducted installation. There it is again. Exhaust from bathrooms and kitchens, dump the fresh air into the return of the furnace. That's assuming, of course, you have a forced air heating system. If you don't have forced air heating, if you have electric baseboard, for example, or radiant heat, then you would exhaust from bathrooms and kitchens and you would duct the fresh air directly to the bedrooms and main living areas. It doesn't have to go to every room. The codes would say to bedrooms, 1 to each bedroom and 1 to the main living area. This also helps with that wood stove scenario or central heat pump because it allows you to distribute air around the house. So there's air movement between the rooms and that helps distribute the heat as well. A very nice solution. And we actually did this First Nations community that happened to be slab on grade, and they simply created in retrofit, they created a drop ceiling in the hallway and they installed the HRV in the laundry closet, bottom right. They exhausted from the kitchens in the bathroom. They created a drop ceiling in the hallway that allowed them to put fresh air into the living room and to the bedrooms. Fairly simple, straightforward retrofit in this application. They had to drop the ceiling about 8 inches in order to get that done. And you might say, well, that's too low. Well, fair enough. If you have a basement, of course, you could install the equipment on the right-hand side there in the basement and simply run into the floor cavities to get you there. So a little bit of a sample. I think you guys all know what these devices are. 2 fans in a box, one bringing in one bringing in fresh air, one taking out stale air, recovering through their energy recovery core, 70% to 80% of the energy difference between the 2 airstreams. So pretty powerful. One issue always is, so where do I install the hoods? I definitely want to make sure wherever I'm pulling the fresh air in, that it is indeed fresh air. I don't want it, next to an exhaust outlet from the dryer, for example. So I always want that fresh air. There's an example. You don't want it pulling behind the barbecue. You'd want it up above. The fresh air is actually on the right-hand side there, up off the ground a little bit. And then on the left-hand side is you have the exhaust from the dryer and from the exhaust from the HRV in the same location. So just give you that one. And then our last slide, I just wanted to speak to for the coastal regions where you have very high moisture levels and not a lot of drying potential. I'm going to say to you, in addition to ventilation, in addition to heating, you need dehumidification. On the coastal regions, a whole house dehumidification system that actually can be ducted in either with if you have a furnace or with your HRV, you would like to have whole house dehumidification to keep you under 55%. And the key number here is if you don't have extended periods of time below 10 degrees Celsius, you need dehumidifiers. For those of you in remote communities, northern communities where it's cold for long periods of time, you probably don't need dehumidifiers because you have really good drying potential. The colder the air is outside, the better the drying potential. But if you're living in relatively mild climates, coastal regions, dehumidifiers is where you'd like to get to. So I know I always talk a little bit too long, but we have about 10 or 11 minutes for questions if that helps.
Hi, Gord, Claude here.
Yeah.
Certainly, we do have a number of comments on the chat. Vince, are you there, Vince? Did you want to talk about energy advisors in Canada?
Oh, wow. Yeah, there was an announcement a couple weeks ago regarding the need for 2,000 new energy advisors in Canada.
Yes.
So this is excellent training, excellent workshop. We're also going to request to our Building Officers Association here in Saskatchewan to include it in their education credits if we can share this webinar with them. I'm sure they'll agree.
Sure.
Yeah, but yeah.
That's fine by me. In terms of the 2,000, yes, they are wanting to identify and train new energy advisors. There's about 700 in the country right now that are qualified through Natural Resources Canada, but they're looking for more, rightly so. And they are absolutely looking for those who want to work in, we'll say, northern communities. And so there is going to be training available. It's a little bit iffy right now as to where you would go for training. But I would say, John, you're going to be good at keeping folks up to date on this and looking for those opportunities. So those of you who are looking to to become a qualified energy rater, energy advisor, by all means, this is a great opportunity to look for that.
Thank you. We have another post here, and it was regarding, could you briefly explain the difference between an HRV and ERV?
Right. Good question. HRV is sort of the historic word. Heat recovery ventilator refers to its ability to capture or recapture, reclaim heat in sensible form. That is the temperature difference between the outdoor air and the indoor air. Pretty simple, right? If it's minus 30 out and it's 70 in, that's a temperature difference of 100 degrees. And I'm going to recover with an HRV 70% of that. In southern climates, let's go to Florida, they worry not so much about the temperature difference, but the moisture difference, right? The humidity. So they look for a device that has a latent component, that is, are able to recover moisture from an airstream. That's called an ERV. An ERV recovers heat in both sensible and latent form. You would want an ERV in a climate where you have high humidity in the summer and your air conditioning. If you're not air conditioning, there's limited value to an ERV. So in your community centers, your office buildings and so on, if you're air conditioning and you're looking to ventilate, ERV makes sense. For most of your community housing, you're going to say, well, we don't typically put in air conditioning. We're in a northern climate. We don't have a lot of air conditioning days. We probably can stay with HRV. The difference between the two now is pretty small in terms of cost. ERVs are almost always slightly more expensive. In terms of operation and maintenance, they both work fine. There's nothing wrong with you putting in ERVs. They will work. I would just say they're not as necessary because they're not as valuable in Canada in general, and certainly northern climates where we're not doing air conditioning.
Are you talking about Florida and California, right?
That's right. That's right.
No,
Not Windsor. We're not talking Windsor as being south. Although in Windsor, if you're air conditioning in Windsor, then you should use an ERV. Absolutely. Yeah. So anytime you have air conditioning, ERVs make sense. And the reason for that is they're not much more expensive. They used to be like twice the price of an HRV, and now they're like $100 more. So if you're
in popularity, HRVs are more efficient than ERVs in most regions in North America.
That's right. Yep.
Yeah.
And then I've seen lots of comment about maintenance, and I understand that fully, that HRVs, you got 2 fans in a box, you got to clean the filters. I get that. And maybe it's not appropriate technology in all your houses. I just want to make it really clear. you need to ventilate your houses. You need either a good quiet bathroom fan, and it too is going to get dirty. The grill's going to get dirty, and it's got to get cleaned.
Yeah,
Or
okay,
so either way, you have to clean, but you need ventilation.
yeah. What if we don't have an HRV? Well, usually windows and doors, right?
I'm okay with that. If you're
There you go.
if your community members are
Yeah.
okay with opening doors and windows, I'm totally good with that. Obviously, that has implications from heating costs, but there's nothing wrong. Let's be really clear. We talked about it last time. Windows used to be the way we ventilated houses, and windows work. Absolutely. Windows are great ventilators.
Yeah.
But we find most people these days are saying, I don't want to leave my windows open all the time because of noise or dust or energy costs. And we're going to say to you, then at least have the ability to have one good quiet exhaust fan in the house. At least.
We're gonna, Harry, did you want to raise a point there? Go ahead. Henry?
Henry?
Hi, thank you very much. I noticed you have direct vents for the kitchen and the bathroom, but in some houses that I've been in, the laundry machine is running all the time. So I'm wondering about a direct to exterior exhaust in the bathroom, in the laundry room as well.
The only thing I would say about that is the laundry, the dryer itself, assuming they have a closed dryer, if you're talking about the closed dryers running all the time, that closed dryer is actually taking about 100 CFM of air out of that room. Now, if they don't have a closed dryer and they're just hanging clothes to dry or hanging clothes outside, you're right. They should have an exhaust port in the laundry room as well.
We're gonna go back.
I just have a quick question, just to interject. CFM means cubic foot meters.
Cubic feet per minute. Thank you for the question. I should always do that. Cubic feet per minute. Think about it as 1 cubic foot is roughly a basketball of air. Think about 15 basketballs of air every minute leaving the kids, being brought into your son's bedroom, for example. That's a little smaller than a cubic foot, but in that order of magnitude. Cubic feet
Yeah,
per minute.
so similar to PSI.
PSI is a pressure. This is a flow. This would be similar to gallons per minute. You know, out of your tap is 10 gallons per minute of water. Out of the HRV, it's 15 cubic feet per minute. It's a volume metric, not a pressure.
I said there's a comment on the chat line that CHVA and B, they're doing energy efficient evaluating training, which I have participated in, and they are doing a good job. But I like to see other provinces do this, do the
Totally agree.
similarities, I guess.
Yeah, I would totally agree. One, Lauren and CHBA, Canadian Home Builders, New Brunswick, always has done a great job of training. You guys are lucky that anybody's down that way. CHBA BC, British Columbia, is also offering training shortly. So watch for that. I don't know what's happening in other provinces, but I know at least on the East Coast and the West Coast, you have the availability of training.
And I think that training is free, I believe, if you're a member, or generally free, if I remember seeing some of the advertisements. So,
well, certainly the intent is to do it very cost effectively. Now that's going to take to the fall. I suspect, you know, when they talk about the 2,000 people they're going to train, that's going to come at a nice cost reduction. But I don't think that'll be set up until the fall. Lauren may know more than I, but
right.
It's going to take a little while to get that set up.
A comment again from Vince regarding on-demand water heaters.
Yes.
With, freeze up issues at -40 plus with wind chills.
Yeah, I get that. You know, the venting of those appliances, the good, well, Vince, it's always tough at -40. You know, it's hard for me to say you won't have any issues. There are some different vent termination kits that can be tried. HRV World's gone through that. Furnace has gone through that. There are some ways to mitigate that, but I get it. At -40, wow, that's tough. That's really tough. And you might be into strip heaters or something to defrost, if you will, those vent pipes. So one, you'd want to make sure it's drained correctly so that it's sloped back to the unit. You don't want it draining to the outside. That's often a problem because there is condensate in that line. You want it draining to the warm side. So it's got to be sloped back towards the appliance, in which case the pipe has to have a drain to it. And then looking at vent terminations that are less susceptible to wind. I get it. It's tough. At -40, not much works.
Okay, we have a comment here, I believe, from Peter, indicating, is it more efficient to connect your bathroom exhausts to a ventilation system?
I get that a lot. Could I put a bathroom fan in and vent it through the ERV or the HRV? And I would say, don't bother. We've done the math. I've done the studies. The bathroom fan doesn't actually boost the flow that much. And I would say don't put in if you're doing an HRV, you don't need a bathroom fan. You would just have the HRV vent from the bathroom and you put up what's called a high speed override switch and you push that and the HRV goes to high speed rather than putting in a bath fan. I would not bother putting the bath fan vent into an HRV. I've measured them. It doesn't help much. And if anything, it hurts because that fan, when it's not on, is restrictive.
Okay, I think kind of to add on to someone else's question, attic ventilation, certainly ridge roof vents and so on, but what about these whole house large fans that sometimes, I guess, exhaust systems you might see in an attic? Are those efficient?
Again, that was a great device designed for the Carolinas. You know, you had a hot day in South Carolina, and then at night you're a little bit in the mountains and it cools off and you want to cool off your house. Okay, they were not designed to run in the winter. You do not want them running in the winter. It's going to cause nothing but problems. But if you're trying to get some, I'll call it free cooling, they can work. But I'm going to say to you, in your climates, open a window. It's a way better choice because the whole house fan, you have to have the windows open while you're running it because it exhausts huge amount of air outside. If you got wood stoves, it's going to backdraft them. It's not a great technology in Canada at all. And because it's really suited for milder climates where they have cool nights and it's really meant to avoid air conditioning. Doesn't help heat the house, doesn't help ventilate the house. They were designed to give you some, what they call free cooling. But other than that, they have all kinds of problems. They're up in the attic, they're electric. You have to insulate over top of them in Canada. The insulation gets frosty and cold. It drips. It needs to be really well air sealed. There's one on the market that you might want to buy in Canada. It's really well insulated, well sealed, but it's very expensive. And you're going to find yourself using it about 3 times a year in July. And you go, why did I do that for 3 nights out of the year? I don't really need that.
Yeah, that is one of the quite curious about these mechanical systems, how they operate in homes and all that. I thought one idea was to improve indoor air quality.
Right. And that's continuous ventilation. That's ERV, HRV, good quiet bathroom fans, not those whole house fans. The whole house fans, that's not what they're designed for. They're way too big, exhaust way too much air for short periods of time. They're not meant as an air quality device. They're meant as a free cooling device. They're not the right approach.
Gord, I've got a question. I have an HRV in my house, and you know that, as I mentioned, I live in Windsor, so I basically shut it down for the most part of July and August because I don't want a lot of humidity coming into the home. So right now, as an example, I'm starting to crank up my dehumidifier, certainly in the basement, to kind of supplement any cooling that's going to take place. Is that kind of a reasonable approach?
Well, from a moisture perspective, I like you running the dehumidifier. I'm still going to ask you, where's your fresh air coming from? Your windows are closed. You know, when you were a kid, you didn't have air conditioning. The windows were open all summer. Then in the 70s and 80s, we started adding air conditioning and people started closing their windows. The air quality in your house is actually worse in the summer than it is in the winter, partly because you don't ventilate because your windows are closed and partly because humidity levels are higher. So I love the fact that you're running a dehumidifier. I'm okay with you running an air conditioner. I would still say, where's your fresh air coming from? Yeah, but I don't want to bring in that hot, humid air. Guess what you'd install? Not an HRV, but a ERV. So you would switch to an ERV.
Thank you very much, Gord. Any other comments before we look at closing off this session?
One of the nannies that living at home in 1928, I got lots of air leaks.
Well,
I always get fresh air.
Who's that talking?
John.
Hold
See,
on. Hold on. I gotta tell you, huge study done by CMHC in 1988. They did like 18,000 children in, I can't remember how many houses, thousands of houses, and found out that the air quality in a 1928 house is worse than the air quality in a brand new house. Why? Because the air's coming in through 100 years worth of dust and rodent activity, 100 years of asphalt impregnated insulations and asbestos and so on. So be careful what you say. In that 1928 house, the reason it had good air quality in 1928, not because it had holes in it, it's because the occupants opened their windows. So if you're saying to me, yeah, I opened my windows, you're good. But if you, the study showed that the leakier the house, the worse the air quality. Sorry.
Interesting.
Yeah, well, my wife would argue with that because you know, we always have the debate. We always have windows cracked, even in
Good.
the
That's
air
fine.
conditioning.
I love that.
But I know that, you know, depending when that season where they're open and closed, we do get these funny drafts. So I actually one time Keith told me just a simple thing: light a few candles and watch the air move. And
Absolutely.
my candles were like on a 45 degree in
There you
in
go.
many of the rooms.
Yep.
So
I love, again, I always like to remind people of this. I actually did a design for a homeowner, a person was building their own house up on the Bruce Peninsula on the what do you call it? The Bruce Trail.
yeah,
And, you know, so he's up high and he's got lots of wind. He said, I don't want to have to put in a mechanical ventilation device. And it's a code requirement. So I actually wrote him a letter, I did a design for him. As an engineer, I'm allowed to stamp that. And I gave it to the local building department because he absolutely was committed to really good natural ventilation. He had windows and window styles and types that captured the winds. And I wrote a note saying these windows needed to be left open and so on. It's absolutely okay to ventilate a house with windows. But if you're not going to use windows, then you have to have mechanical ventilation because to rely on leaks through holes, electrical outlets, you know, I always say we didn't put that third prong in the electrical outlet to get us more fresh air, right? We never got fresh air through electrical outlets. That's not fresh air. That's fibrous, that's mold, that's dust, that's bugs. Windows are fresh air most days, and ventilation systems like HRVs or bathroom fans are good ventilation. But relying on holes and cracks does not guarantee you good air quality.
Hello,
I
Gord.
agree.
Go ahead.
Hello, Gord. It's Dave from Prince Albert here. My question to you, with an HRV and you're drawing from the bathroom and the kitchen and no supplemental fans like the range hood or the bathroom ceiling fan, how do you get as a building code guy, how do you get, I've run into issues because the building, it actually says the damper in the HRV is in place, but sometimes the developed length between the HRV and the bathroom is a long, it's quite long.
Sure.
How, how do I get the installer and whatnot without me actually doing to make sure the right CFMs are coming out of that area? Do you sort of know where
Yeah.
I'm trying to get at?
I sure do, Dave.
Like the minimum capacity for the
Yep.
bathroom or kitchen.
Yeah.
I've have huge issues with that. I run into that constantly, and I don't know how to address it.
Right. Again, I really appreciate the question. I went out to a house just 5 minutes from where I am, a brand new house, 2-story house, 2,200 square feet, 3 bathrooms, laundry room, kitchen, all pulling from the HRV. And he's complaining in his bathroom or their bathroom, the longest run, clearly the longest run from the HRV is drawing the least amount of air. Well, that's physics. You're right. So to my mind, you balance, that is, you have adjustable grills. So the ones that are closer, you balance those down. But fundamentally, Dave, the National Building Code, if you look at the National Building Code, there is a section in the 932 that says if the duct is longer than this, it has to be 4-inch. If it's longer than this, it has to be 5-inch. If it's longer than this, it has to be 6-inch in diameter. So we have pretty good confidence, Dave, that if you follow those prescriptive requirements, you will get enough airflow out of each room. You might need to balance, that is, turn the dampers down a little bit on the ones that are closer, but we've had pretty good success, unless you're talking, well, I don't know how many exhaust ports. You'd have a couple of bathrooms and a kitchen and a laundry room, sort of 3 or 4 vents. Is that?
Yeah, yes, 3 or 4,
Yeah.
but the code just says a damper, but then it says the damper on the HRV, that's considered a damper, right?
Okay, no, you're right.
Not on.
You want them adjustable. So they have those round white grills that are adjustable. You turn them. That's what I would have and say to the contractor, I want adjustable grills in the bathrooms in the kitchen so that I can turn some of them down so the others get more airflow. Air always takes the path of least resistance. If you turn some of them down, you'll get more air at the other end. So first it's right size HRV. Second, it's right size duct. Third, it's a balancing grill in each location or an
So just-
adjustable grill.
But the NBC does not say an adjustable grill.
No, you're absolutely right. As a
So-
minimum, it doesn't say it.
So
But
that's,
you-
so
Yeah.
I've got some smart installers out there, and that's where my issues. I can't write a report if I can't reference the F326 or the NBC. That's
Yeah, fair
just the
enough.
way I'm. So
So in that case, Dave, you're within your rights to say to them, all right, show me the measurement, because the code says got to be 20 CFM from the bathroom, got to be 60 CFM from the kitchen. So if you don't want to put in the damper grill, I'm going to make you measure every system. It's right there in the code. You have to measure it. So
fair enough, thank you.
you could try that. I would say, well, I know it's difficult. I always with trades, they always, we would say they want to do the minimum because they don't think anybody wants to pay for more than the minimum. But I would say switch to adjustable grills. It's an extra $3 a grill.
Thank you, Gordon. Thanks everyone for the questions. It's time to wrap up the session. I think most of us, if not everybody, got a lot out of the session. So I have to thank you very much, Gord, again, making us a little bit wiser, more knowledgeable about HVAC systems. Certainly a very interesting perspective for each of us to think about.
Yeah, thanks, Gord. And so Monday, we have risk and construction. And then on the following Thursday, the 10th, we have the Canadian Construction Documents Committee. And they're talking about the use of contracts and their documents, which is, I think, really critical for many of us to understand contracting and project management. And then, just looking at June here, we have one on estimating and costing. I believe that's Claude. And then we have Gord back again for passive housing and building performance. So thanks, everyone. Enjoy the weekend, and we're touch base on Monday. Thanks again, Gord. Wonderful.
Thank you for the opportunity. I really appreciate it. Thanks, guys, for your questions. That's the most important to me.
Yeah.
Thanks.